Okay, hi. We're going to be getting into something called Riemann sums, which is a big, very important part of the calculus curriculum. And we're going to be talking about really two different topics today. The first one is approximating areas under curves using a Riemann sum. And the second is we're going to do a little bit kind of review on summation notation. So we'll start with the Riemann sums and we'll do a little bit of summation notation. I'm going to break this into two different videos, I think. Oh, here we go. Okay. So first of all, let's just state our goal. Our goal is to figure out the area underneath the curve. So this is our curve, f of x. Oh, f of x. Okay. Our curve f of x. And this is from a value a to b underneath the curve. So I'm looking for this shaded area. And for the purposes of this, it's not always true for these kinds of problems for Riemann sums. But for this kind of problem, we're gonna assume that f of x is positive. So we're gonna let f of x be positive. Okay, so we have to think about how we can actually do this. Okay, if we're gonna break this up into and get an area here under some kind of oblique, some kind of strange shape, what do we do? Okay, and typically what we decide to do is to break this up into smaller shapes. Okay, so for instance, let's try this. What if we were to break this up and find the area of each one of these little spaces here? Okay. Well, the problem obviously is that we still don't know how to find the area, pardon me, of this shape right here. Okay, or this shape right here. Okay. However, these are fairly close to rectangles. Okay. So maybe I could look at this rectangle. I find the area of this rectangle from here. Okay, this stuff in here. Or maybe, let's say, maybe this rectangle here, the one that goes across like, oh, you see what I'm trying to draw, right? It goes across like that. There we go. And maybe this rectangle here, and this rectangle, that's kind of not a very good rectangle to use, and then that rectangle. So maybe we just try to find the area of these rectangles, and all the rectangle is going to be base, this length here, times height. Okay, base times height. You can imagine there might be other shapes we could choose instead. For instance, we could choose maybe like some kind of trapezoid from here, get like this shape here, which is kind of like a trapezoid. Okay, that might work too. But what if we break this area up into shapes that we're able to actually find the area of? Okay, and that's what we're going to do. Okay, so let's go ahead and start with that. So here's the idea. We're going to divide the region up into intervals of equal length. Okay, so the length of each interval will be b minus a over n. We're looking at, and I guess I should say, we're looking at an interval from a to b. Okay, so the length of the interval is going to be b minus a over n. Okay, so the entire interval obviously is b minus a, but the length of each individual subinterval is b minus a over n. Okay, and oftentimes we'll call this length delta x. Okay, so if we go back here, what we're saying is that if we divide a to b, pardon me, up into a bunch of little subregions, just to make it easy, we'll make all the subregions or subintervals equal length. The length of each of them is going to be b minus a over the number of intervals. Okay, all right. So the length of each of those intervals is going to be delta x, which is b minus a over n. Okay. If our interval is a to b, then our subintervals are marked by these numbers. We start with a. The next number over is going to be a plus one of these lengths, then a plus two of these lengths, then a plus three of these lengths, all the way up till there are n of them, so a plus n of the lengths. Okay. But also notice here, the last marker is the number b. This number here is b, so we go from a to b because this here, okay, is n times b minus a over n. Those cancel. We have a plus b minus a, which is b. Okay. All right, moving on. Okay, so now we have to figure out, we're going to make these rectangles like we saw in that picture, right? We're dividing up into little intervals, and then we're going to make each one of them a vertical rectangle. So how do we decide what the height of that rectangle should be? Okay. And so the question is, do we decide to use, let's see, okay. Do we decide to use, if I divide it up into a bunch of different intervals here, do I decide to make the height of the rectangle the height at the right end of the interval? Do I decide to make it the height at the left end of the interval, or do I decide to make it somewhere in the middle of the interval? How tall do I make this, right? And it would be great to make the decision every single time. Okay, let's look at this one. This one would be good on the left. This would be good on the right. This would be good on the right. This would be good on the left, right? It would be good to be able to do that. But what we're going to try to do is we're going to try to make it standard. Okay? So here are different pictures, right? Here would be going from A to B with 4 sub-intervals, okay, measuring the height on the left. This would be 4 sub-intervals measuring the height on the right. And this would be 4 sub-intervals measuring the height in the middle. And you notice that each one of these is going to approximate the area from A to B underneath this f of x, but they're all going to do it a little differently. This one's probably going to be the best. Okay, this would be an over estimate, and this would be an under estimate. Okay, so just something to kind of keep in mind here. Now, we're going to go ahead and we're going to start by looking at the the right endpoint estimate. Okay, and we're going to do each of these. Okay, this is a left endpoint estimate, this is a right endpoint estimate, and this is a midpoint estimate. We're going to start with the right endpoint approximation. Okay, so we're going to add up the rectangles with the height given by the right endpoint. Okay, so I'm going to take the length here, which is delta x, so we have right here, and take the length times the height. Okay, and we're looking at length times the height. And the height is given by the right endpoint of the first subinterval, which is not the height of A, but the height of A plus delta x, right here. Let's move to highlighter. A plus delta x. Oh, that's our large highlighter. Okay. There we go. Okay, so that's the first rectangle. The second rectangle will be the same length, always length delta x, because every interval is the same length, times the height f of the right endpoint of the second interval. Okay, this is the right endpoint of the second interval. Okay. Plus, and we keep on going until we all the way get to the end, no matter how many subintervals we have. And the last time, we're going to plug in the last endpoint, which is actually b, right? This is actually the same as b. But for the sake of consistency here, I'm going to write it as a plus n of these subinterval lengths. So I plug that in to get a height, and I multiply that by the length of the interval. Okay? So this is going to give us an approximation for the area under the curve using rectangles that are calculated on the right endpoint of each of the subintervals. And so notice I can factor out a delta x because every one of these terms is multiplied by a delta x. So this is really the formula we're going to use most often, is the one down here. The right endpoint approximation with n subintervals is given by the length of each subinterval times the sum of the right endpoints of each interval. That's what that says. All right. Let's try one. We're going to find the right endpoint approximations for the area under x squared on the interval 1 to 3 with 4 subintervals. So I'll just sketch this real quick. Okay. We're looking at x squared. We're going from 1 to 3. So I'm looking for an area like this. It's kind of not a great picture, but you get the basic concept. I'm looking for this area. And what I'm going to do is I'm going to divide this area up into 4 intervals. 2, 3, 1, 2, 3, 4. Good. And on each of them, I'm going to use a right endpoint approximation. Not the best picture, I might add, to get the area. So first of all, 4 subintervals means the length of each interval must be 3 minus 1, divided by the number of intervals. So I get 3 minus 1 over 4, which is a half. So if I'm going from 1 to 3 and I divide it into 4 equal parts, the length of each equal part is a half. It's pretty straightforward. Okay. Now, this is kind of a slightly new notation, but bear with me here. I'm going to start at the left endpoint, A. Okay, and to get to the next interval, I'm going to add j copies of a half. Okay, and j is going to be, since there are 4 intervals, it's going to be 1 to 4. Okay, so I start with the left interval is going to be 1, then I add 1 half, then I add 2 halves, then I add 3 halves, then finally to get to the right endpoint I add 4 halves. Okay, so this is what it looks like. I start with the left interval, which is 1. Okay. Then I add a half, right? So 1 plus 1, 1 plus 1 times a half. Then I get to the next endpoint by going 1 plus 2 halves. Then I go 1 plus 3 halves, 1 plus 4 halves, and notice at the end we're at the number 3. So the first endpoint is, or the left endpoint is 1. Then we get 1.5. Then we get 2. Then we get 2.5. Then we get 3. Notice, right? So it goes 1, 1.5, 2, 2.5, 3. And again, you could obviously figure that out on your own. I'm trying to make kind of a systematic way of doing this every time. Okay, so here's what I have to do. I'm going to take the length of delta x, which is a half. I'm going to multiply that. This is the formula for r sub 4. I'm going to multiply that by the sum of the values I get when I plug in on the right endpoint. Right? So I don't plug in the number 1 because that's a left endpoint, but I do plug in the number 1.5, and the number 2, and the number 3.5. Sorry, the number 2.5 and the number 3. Okay. So an approximation for the area under the curve from 1 to 3 is going to be 1/2 times 3 halves squared plus 2 squared plus 5 halves squared plus 3 squared. If I square those and add them up and multiply by a half, I'm going to get 43 thirds, which is 10.75. Okay.